Okay, we can start now. If you can confirm that the presentation view is visible.
Yeah, all good.
Okay, thanks a lot.
Yeah, thank you.
So let's continue from where we had stopped last time. I would like to close the previous topic on just some general background on power and energy issues in computing systems. We looked at some of the architectural aspects at the processor, memory, and cache level. We'll continue and close that topic today with again a glimpse into a few other levels of abstraction, little higher levels of abstraction at which this is applicable power issues, power awareness. It would be great if we can have some of that. So that would be the first part, and the concluding part, which is really the agenda for today, would be the thermal awareness. The temperature sort of comes in as a related but still slightly different issue. Whose awareness actually is interesting, it's important, and also we'll see that it leads to several newer system design opportunities, optimization opportunities. That's the topic that we'll also continue today into the afternoon lab, where we have for you a simulation system that combines performance simulation, power and energy on one side, and also a thermal simulation that represents some joint work that we had done actually with other collaborators. I'll refer to it later in this talk. So the afternoon session we'll spend on trying to experiment just with a couple of different policies and see what impact it has on thermal profiles of our memory systems. That specifically, that's what we'll be talking about. But hopefully through the introduction in the discussion in the morning and through some hands-on experience in the afternoon, we'll get some just some basic idea about some of the interesting issues that come up, specifically there in the context of emerging memory technologies. They are all interesting, they are great with respect to some properties, but they also create some other challenges, thermal being one of them, and that's the agenda for the day. So let's continue from where we started off. At the software level, what kind of power awareness is possible? Again, the treatment will be similar to what we did in the previous lecture. That is, we'll take some example, very specific examples of transformations and optimizations so that the point is made. It is not a comprehensive treatment and no major theory is involved here, but yet the examples that we are talking about should all be hopefully accessible to all of us. Okay, so just a few stones, starting off with some of the early optimizations that people came up with in this area. Now the compiler generates an instruction sequence from high-level code, and what kind of power optimization opportunities are there in this space? The physical mechanisms remain the same. Dynamic power refers to power dissipation due to activity. So if you can reduce that activity in some way, of course, that would be good. So how can you do that? We'll look at a few examples. The sequence of instructions that goes out may make a difference. These were just some of the early recognition of possibilities. If you can compress in some ways instructions or data, that also might give us some opportunities for saving power because we could fit them into smaller memories, and that might actually help us save, if nothing else, leakage power. So this is the static power, which we could save in various intelligent ways by intelligently turning units off when they are not needed, or taking them down to some sleep state or low power state. Function units can be gated in various ways for their power, and that might actually help us in saving power. The implementation of this is, of course, something that involves our architectures. They ought to enable the control that we now want to exercise in software, but assuming such control is there, let's look at what kind of opportunities are there. Now, one of the early things, opportunities in this region that was sort of identified and sort of lays some of the early foundations. Although not specifically this specific optimization, it is not clear how much it is applicable. I mean, this is implementation dependent. Nevertheless, it illustrates an important dynamic power optimization possibilities, where an instruction register takes some value. In the next clock cycle, it takes some other value, and the Hamming distance between the successive values of that register, corresponding to the number of bits that changed from one cycle to the other, is something that measures dynamic activity, right? Which leads to power consumption. This is more of a principle thing that I just wanted to illustrate here, not necessarily that something that explicitly is applicable in an independent sense. A lot of these things do depend on the particular implementation details and so on. We won't look at them, but then reducing Hamming distance between successive values on some storage or some bus and so on. This is still an important conceptual thing whose awareness is important with respect to reducing dynamic power. In this case, specifically what we are seeing is that if you look at that opcode field and to the new opcode field, these are two different instructions, and therefore the opcodes are different. And the change in the number of bits. So ideally, we would like to minimize the number of changes in the bits. Similarly, if you look at these register, source and destination, again here, it would be good if we can do something to reduce the total number of bits that are transitioning, for example. Such problems tend to this is an illustration of a general class of problems where the objective would be, in the interest of saving dynamic power, we try to reduce the total number of bits transitioning. These are the sort of low-level optimizations that people started off. This is an application of that principle. But what could you do? You could schedule instructions, assuming you had the choice. So that the total number of transitioning bits could be reduced. You could choose appropriate opcode if you had that choice. In application-specific processors, you might have that choice, and therefore you might intelligently use that. Exercise that choice. Choose appropriate opcodes so that your instruction sequence has a minimal number of bits that are transitioning. Same thing about the register side. You could maybe rename registers keeping this in mind. Remember, as we are talking about this, that this is really a more general concept. The particular instance here is with respect to instruction sequencing. It may or may not apply. Most of the times it might not apply, but nevertheless, the principle is important. That's why I just wanted to put this up. Power gating is an important optimization. Some function units may be unused for long time periods, and that information is something that is available to the compiler for an individual program. This information is incomplete, of course, because the compiler doesn't know about what other applications are also running at the same time. So there's sometimes a very fine sort of a complementary knowledge that is there between the runtime system and the compiler. The compiler has some future knowledge of an application. Right, because we are able to see the loops, we are able to see what code comes ahead and so on. So some view we have about the future, but the runtime system in some complementary way doesn't have that future as much of an insight into the future of individual applications, but to compensate, it has some view into what other things are happening at runtime, which sometimes, of course, the compiler has limited awareness. So the possibility to power gate the idle FUs is something that could be identified for a compiler with respect to the specific program that is being run. Now, of course, so idea is that you could do the analysis at some higher level of granularity, maybe at the loop level. And if you find that certain kinds of operations are never going to be performed in that loop, you could actually pass on that hint that you could power gate some unnecessary CPUs, if assuming some special instruction is available, and expose that in some ways so that the runtime system can take a decision. If it is safe to do so, if other processes that are running at the same time also have a similar property, then we could save power by gating FUs, function units that are recognized to be idle. Various instruction set customization possibilities could exist. That's what our ASIP is, application-specific processors, where both the architecture and correspondingly the compiler are customized for an application. If some instruction sequences occur frequently, then we could combine them into special instruction, which could be faster, it could be lower power, because there is some optimization that we have done for a group of instructions. So when we do that, how do we save power or performance? We could, because it is an application specific instruction that we design, it is a customized instruction. Of course, it might be a more complex instruction and so on, but point is there would be no need for a separate fetch and so on, all the stages that an individual instruction would go through. So the possibility is there. It could be exploited in a context like this. Quickly, if we can move on to a few other possibilities. So that was about the possibility of customizing instruction in an application specific way. That's where a compiler, along with the runtime system, of course, can play a role, and some power awareness, energy awareness could be brought into the field. There are a bunch of transformations that compilers perform, or of course these are software transformations, so they could be performed in by the application programmer also. Either way, there are many of these, and these transformations are very interesting in the sense that they are heavily studied, their applicability is well known, performance related advantages are well known, and yet when it comes to power, some interesting implications could be there. Let's just study that through this simple example here. The idea is you have these two loops for I is equal to 1 to n. There is some initialization happening of an array, and in the other loop you have a second array. The loop structure is the same, but there is a different array that's being accessed. Okay, there's a standard loop fusion transformation, which is that we combine these two into one bigger loop in which the two bodies are merged. Of course, appropriate care has to be taken. Only if it is safe to do so, we should be doing that. Nevertheless, in this example, it is clear that it is safe, and therefore we go ahead and combine the loops. That's what we call fusion of the loops. Conversely, you could start from this and perform the reverse transformation, which is called fission, which all that we have done is taken the more complex loop body and split it into two individual loops. Okay, both these directions are possible. It doesn't matter what the user specified the program. Maybe specification was one, but we have the opportunity of transforming our code in either in one direction, the forward direction, or the reverse direction. So all of that could be done. The question really is, which is the correct one, which is the more efficient one. In general, it's actually hard to identify what direction is actually good, but let's outline some, try to identify some advantages of the forward direction from here to there, the loop fusion. From a performance point of view, this seems like an attractive idea. Because at the very least, here is what is happening. These two different loops have this condition check. So since there are n of these condition checks that are happening, right, the less than check and this increment, these are happening n times here and n times here, so there's a total of 2n of those checks that are happening here. Because you have combined the loops, the number of conditionals is lower, so in general you can expect that the number of instructions is lower, and therefore it is a faster. So possibly from a performance point of view, this is actually a good idea to go in the forward direction. The body is not changing much. This is the same. Here too there might be some optimization, like the offset at the A and the offset at B. Those are similar, and that similar offset can be used here. But let's assume that this not much is changing. It's the same loop body that we have just fused. But it's very clear that from a conditional point of view, this second one is better. But actually, some of what I want to illustrate through this is a lot depends on what else is happening in our memory system. For example, there could be some instance in which it depends on the context, but it is possible to think of some contexts based on what is happening in our memory system, where the reverse actually might be a good idea. Here is an example. Suppose these are very large arrays, and they are, and we know that they're going to be stored on disks. Then here is a possibility that you could maybe A is residing on one disk and B is residing on a different disk, and it's possible that you arrange your computation in this way that one of the disks is idle when one loop is on, and when the other loop is executing, the second disk is idle. So whereas in the fused loop, both the disks are busy throughout the execution of the loop. So considering that this is the possibility, which is better? It seems as though loop fission, which is the reverse optimization, reverse transformation, that would be preferable, because we could save power by setting the idle disk into low power mode, whereas maybe in that other context, both of these are busy. There is no chance of saving that. So again, this is an illustration of something that is possible. This is more of a conceptual optimization really, but what it's pointing out is that that there are several such possibilities. If we understand the way our data is organized, if we understand our memory system well enough, then we can identify optimizations for saving power and energy, and identify also, in addition, trade-offs that exist between performance optimizations and energy and power optimizations that it's good to have awareness of at the system level. One could go on. There are a large number of these transformations. Many of them classically have been proposed in the context of performance, and indeed there is an opportunity to redesign some of these, take a second look at some of these optimizations and convince ourselves that it's actually something that still makes sense from an energy point of view, or does it represent some kind of a trade-off, and if so, then we make an intelligent choice, right? So that's really the message in studying these transformations. Again, we won't be able to go through all the transformations, but there is a large body of literature consisting of loop transformations performed by a compiler. Invariably, they were all targeted originally towards performance, sometimes at code size, but largely at performance. Sometimes they also take into consideration several other architectural parameters like cache sizes and so on. But the idea was really to get programs to be faster. But with the newer metric in front of us, energy or power, and later on maybe even thermal issues, the there's an opportunity for us to take another look at many of those transformations and study for ourselves whether it really still makes sense. Is what was good for performance, is it also good for energy, or is it bad for energy? Because often these things are trade-offs. Right? Early on, we of course pointed out that if you are saving power, if you're aggressively saving power, chances are that you are compromising on performance in some way. But it is a trade-off that is important to study for us. This is an example of a standard transformation, scalar expansion, that removes artificial dependencies in the following way. You have this kind of loop. It looks simple enough. You're essentially assigning t equals ai and bi. So these are three different arrays, and you do some computation and write the result into a third array. Now, this by itself, you can see that there is some parallelism in this loop, right? There is no dependence across the loop iterations, but in a naive way, it might appear that that scalar variable is being reused, and it prevents parallelization for an obvious transformation. So one standard way to get around this is you just transform that into an array. Right, so you don't need it. This is good enough. You don't need the array variable here, but that array, if you expand it into an array, it is sort of a nicely vectorizable transformation. So this is classically recognized as an important optimization. If you have a vector processor, then this is actually good. A vector processor with a vector register file and memory system and so on, then this is something that is good. But we should really be taking a look at such kind of transformations if we want to a second look at these transformations to make sure that they still make sense in a different context. If I want to save power, does it make sense? For example, what was earlier a scalar variable may be obtained from a scalar register. If that now translates to a vector data that is obtained from memory, then there may be extra cost involved with respect to energy, for example. In our specific instance, it may make sense, it may not make sense. Whether specific optimizations, transformations like this make sense or not in the context of power and energy is an open question, and it's an interesting question now that the metrics are different. Let me also point out some other opportunities that exist. The context here is some compression. The opportunity is that if we compress our instructions or data, then we can use smaller memories. Now, smaller memories translate to power savings. Why is that so? It is, this is an important observation from the point of view of both the leakage power and dynamic power. Leakage power tends to be independent of what activity you are doing, but it is a function of the area of the memory. So smaller memory means lower energy footprint as far as the leakage is concerned, and therefore it's a good idea. Now, dynamic power is also smaller because the energy per access of the smaller memory is less than the energy per access of the larger memory. So it seems that it's at least in concept it should be explored. The tricky part of it is to get the implementation efficient, but nevertheless the opportunity should be understood. So here's what we could possibly do. Various kinds of instruction compression could be performed, but here is a general observation. Even though a processor might actually provide a large number of instructions, typically in our programs, only a small subset is likely to be used. This is just true the way programs are written. Right? Frequency is not equal of all the or instructions, and therefore that might actually, such asymmetry often permits compression in some nice way. So we can encode maybe instructions in some different ways to exploit such kind of distribution of instructions in typical programs. What could I do? Here's a simple compression mechanism. Normally it was an 8-bit opcode. 8-bit opcode would support 256 instructions, but here is a compressed version in which I just use only 4 bits. So let's say only 8 of my instructions out of the 256 were heavily used. So let me use 4 bits. That first bit can tell me whether it is the compressed format or the normal format. So if it is a 0, then I use the compressed format instruction. Otherwise, I would use a 9 bits and use the regular instruction format. So compressed. So if it happens that most of my instructions are actually one of those 8 that correspond to the compressed 4-bit opcode, then you can see that I can save some space for my instruction memory by essentially compressing my 8-bit opcode to just a 4-bit opcode. That's about instructions. I could also compress data, but that is slightly orthogonal. We won't be looking at that. So nevertheless, that's a possibility. And overall, the people have studied the implications of instruction compression, data compression. Such things are conceptually easy to say, but they are a little tricky to implement because remember, there is some overhead that is involved, compression and decompression at runtime. If you are going to do, then there is some power overhead because of the decompression itself, right? Even if compression is done offline, decompression is online, and therefore there is some additional power. So what power you are saving could actually be offset by that overhead. So it is a little tricky, but nevertheless, the possibility is there. Some interesting architectural problems come up when you try to implement such systems. Where does the decompressor lie? Maybe it is between memory and cache. Okay, DRAM and cache. So that's where the decompression happens. There are some advantages to this. This is activated only when there's a miss. But the thing is that the cache is now going to store uncompressed instructions. So I need a larger cache. Conversely, I could have the decompression block here between the cache and the CPU. I mean, the rest of the pipeline. That has some advantages and disadvantages. The advantage is that the cache can have compressed instructions, and therefore the cache could be smaller. But then my decompression overhead is there for every instruction that I'm fetching from the cache. So there is some trade-off here. These different possibilities have been studied, but the thing is, even though such ideas appear conceptually elegant, the implementation is not as simple. There are also other interesting issues due to addressing and so on that I'm going to skip here, but I just wanted to point out that compression in general is something that could be useful from a power point of view, and in various contexts people have studied and implemented such systems. So an example of a commercial implementation in a context like this is there in the ARM system. There are normal instructions. There are also reduced bitwidth instructions that correspond to lower power, and there would be some way for us to explicitly switch between the regular instruction and the compressed instruction. So the difference is that there's a difference in the width. So regular instruction would be 32 bits wide, and this one would be 16 bits wide. You can see that the number of instructions supported here would be less because it has to fit into that. And similarly, there are other restrictions. Similarly, the effective register file that is available could also be less just because the number of addressing bits have reduced for the register. But nevertheless, this opportunity is there. If the compiler does the analysis and decides that, okay, for this section of the code, which is actually an important section because it's a loop that's going to be executed many times, If I can do with the narrower instruction format, which is the compressed instruction format, then that could actually lead to a low power implementation of the same low power execution of the same program. So this does have some serious and practical implications, not merely a theoretical idea here. Okay, so that was the extent to which I wanted to discuss the compiler and the software level interventions when it comes to power and energy. Let me proceed at a similar level of detail into some other interesting contexts in which power and energy are things that are worth being aware of, and that's in the relatively larger system servers and data centers. Again, these are some of the early ideas that were explored in contexts like that. So power is still like a relatively recent concern. These were performance oriented traditionally, and here are some interesting things. The concentration of a large number of powerful machines in a small area, that's what you see in data centers, right? It improves the operational efficiency and so on. But of course, there is some concentration of power because of that, and it's worth worrying about power management at a larger scale than the individual machines that we looked at because of this. So that's the motivation for looking at power management at server, cluster, data center. So bigger levels of abstraction. Again, the basic ideas are not very different. We had identified DVFS and power gating and clock gating, and so those kind of mechanisms, shutting down portions of the system so that we can save power. Those ideas are still the same, but just that our systems are now much bigger systems than they were. So various things come into the picture. Some of them are new. First of all, how do you characterize the systems for power? You could look at the characterized individual components. This is some example system that people studied at some time long ago. But let's say I add up all of this, and it comes to 213 watts, and the AC power that it translates to is something like this. So I could just read off, and a particular machine, a server machine, let us say, that is running. I conclude that okay, that's the what is called the nameplate or the rated power. But often you would find that if you actually run the system, your measured power would be very different from the rated power, which might be an overestimate or an overkill if you just add all the modules together. Because typically, if I say this is 80 or power here is 12, we might be overestimating that. It might be the max power that we are counting, and it would be incorrect to add all the maximum powers of the different components and take that as the rated power. I mean, it is a safe rated power, safe power limit, of course, but in fact, it might never happen that all those components are operating at the highest level of the power. Right, so there is often a difference between the installed capacity and the utilized capacity, because the actual equipment the power due to the actual equipment might be lower than what is provisioned for. Various interesting problems come up in a space like this. Let us say this is a server system that is responding to a request that is getting from all over the world. All over the world, or a particular region, or whatever it is. There might be a utilization curve like this depending on the time of the day. Okay, so this just corresponds to the utilization being relatively low during off-peak hours and relatively high during the peak hours of or maybe these are office hours. A lot of people are using it in early morning or late at night. There's not much use. So that's a system for us to understand and optimize. You can see that that low utilization, because this variation in the utilization maybe gives us some opportunity for saving power. For example, why should I keep machines on if I already have some expectation about the expected utilization, right? So that's one. If I just look at the power delivery chain, right? This is an old picture, but while the absolute numbers might be different, it tells a story that is actually interesting, which is there are inefficiencies, power losses along the way, right? What you are actually drawing maybe something like 200 watts. There are all these UPS is going to lead to some efficiency, some loss of power. Power distribution system leads to some other loss of power. Closer to the machine, that power supply leads to, so these are the efficiencies, right? So there's a lot of power that is lost along the transmission chain, all the way to that DC to DC conversion. Finally, what we started off here might be like 250 volts. What these systems components are operating at might be like 1 volt or less than that. And so because of these power conversions, there is actually a huge amount of power loss. What you're delivering to the system is only 100 watts, whereas what you're drawing is much more than that. When such when this is the physical characteristic of the system, you could actually exploit that in some way. We'll see what to do about it. The idea of frequency scaling is known to us. You choose from different power states and clock frequencies. In the multi-core systems, the frequency of different cores can be independently controlled, and our objectives may vary. We need to deliver the highest speed. But that's only one kind of metric. It could be instead that I deliver higher speed under a power constraint. Right? Why power constraint? Because infrastructure constraints might be there. Maybe we want to deliver the highest performance at the lowest energy because the battery is something that needs to be optimized. So these objectives may vary, and in a system like this, where we have some understanding of the power model of the system, where in this server sort of systems, it's very likely that your idle power is actually very high, which is at zero utilization, just you're keeping the system on, and yet what you're consuming is pretty high, something like 50–60% of the peak power. At 100, it goes on, not necessarily linearly, but yeah, it's a decent model for if you want to make it as part of an algorithm or optimization problem, for example. So we studied that power supply leads to inefficiencies, but there is some interesting characteristic there. It is not uniform. That efficiency may depend upon the load. These systems are designed to be efficient at high load, relatively high load, so maybe like 80%, 100% use. It might actually be efficient, but the efficiency might actually fall off sharply if it is in the lower region, if the load is not very high. These are the characteristics of the systems, of those power supplies that are designed by us. And such things, if we have some awareness of this, then we could actually take advantage of it in the following way. There could be some consolidation that we do of the server systems in this way. So let's say I am in this part of the day, right, in which I know that the utilization is not going to be very high. So then here is our choice. We could divide our load in the following way, divide it in a balanced way between our 4 CPUs, if that's what our system is. Alternatively, we could increase the load. Instead of keeping them at 60%, we could actually increase them to 80% utilization, which is actually better from the power supply point of view because it is operating in the more efficient region there. But advantage is that the same amount of work is being done by 3 of the processors, and that gives me the opportunities of maybe switching one of these processes off. So there is some imbalance in the distribution of the load, but that gives us some opportunity to save power, which wasn't there earlier. So such things, again, this is a simple, simplistic and conceptual picture, but the principle is something that we could use here in a more sophisticated optimization that might translate to something like this. This is called a power capping or a thresholding optimization. Applies to the server class, where normally you have provisioned a certain capacity, right? So many, that capacity corresponds to so many machines that the system that are part of the system, and therefore there is of course power that is wasted because of excess capacity. If the utilized capacity is small, 10%, and 90% is unused, that is the excess capacity. If that capacity is held constant, then that's a bad thing, because I'm delivering my performance fine, but then there is an energy loss in the system. But I could think of designing this differently. I could respond to the load actively instead of just keeping the capacity constant. I could turn my systems on and off as and when the utilization uh, threshold is crossed. So let's say I divide it into 5 regions, and if I cross this first 1/5, then I turn on a new set of machines. If that's also, if I exceed, let's say, the 40%, then maybe another bunch of machines are turned on, and so on. So I could respond in a dynamic way. That way, the excess capacity is minimized, and the excess power is also minimized as a result of that. Of course, this is also a little bit simplistic picture. Your realistic picture might be somewhere in between, which is that you have provisioned a little bit of excess capacity, but not too much more. For example, you can add new capacity when the load here reaches maybe 80% of the current capacity, anticipating that it might exceed the 100%. When we say capacity here, it could translate to different things, but among other things, it could translate to just the number of machines that we are keeping on or off. So yeah, that's these are just some simple examples of power related concerns, and just of course at a principle level, but ideas that that were identified early on and followed up into management of power and energy of larger scale systems. Okay, so to conclude this part, the power and energy part of our discussion, these energy and power optimizations are at different, they are applicable at different component and levels of abstraction. In the previous week, we looked at processor and memory and cache context, where it applies. And today we concluded that discussion with some view on the what the compiler can do or an application programmer could do, and also at a little higher level of abstraction, what can we do at the level of servers and data centers. If there's one thing to remember in all this power and energy discussion, it is that you almost always have a very fine trade-off between performance and power. You don't get the power saving for free most of the time. Usually there might be a small impact on performance, but that might actually be acceptable. Remember, when we started off this discussion, we talked about what are the right metrics. Energy, if that's a metric, or energy delay product, if that's a metric, that of course in a nice way captures both the performance and the power characteristics of the system, so that a trade-off does show up in a single metric like energy or energy delay product or energy square delay product, and so on. Any of those, of course, which one you use does depend on the context, the kind of system that you have, the kind of service that you are providing, and so on. But that trade-off needs to be understood. Okay, so I'll conclude the discussion with some interesting thermal issues. This is a topic that's independently interesting. Obviously, the thermal and temperature matters are related to power and energy, so they are not completely independent. But nevertheless, there is a strong dependence. But in addition, so to recognizing that there is a relationship, the point that I would like to make here in this discussion is that in spite of the obvious relationship, there are a new set of issues, new challenges, new opportunities that come up if you bring thermal awareness into the system. Again, our systems are the same class of systems, CPU memory. There's nothing otherwise fancy that is happening. But then these technologies have been evolving, and let's look at a specific context here to understand, to appreciate some of these issues. The related concern here being temperature is that we can't allow temperature to exceed a threshold. And what's interesting is, let's say we're talking about a processor or a memory. The processor is a complex system. The chip is large, but issue with temperature is that the temperature cannot be allowed to exceed a threshold in any part of the chip. It's unlike power, which you take the sum of the power of all the different components. When you calculate energy, again, you calculate the sum of the energies of all the different components. Here we are not interested merely in the sum, and of course it doesn't make sense to add the temperatures, but we are interested in, we are monitoring closely the temperature of every part of the chip, every system, every subsystem, every component we are worried about. And if it turns out, so the system fails if the temperature exceeds the allowed threshold on any of those components. So in some ways, it is it's sort of a different awareness, even though it is a related thing. These are heat and temperature and power and energy. These all seem to be related, and yet the kind of actions that we take might actually be different. Here, why is it that temperature needs to remain within the threshold? It is that packaging concerns are there. The packaging material is assuming that your chip temperature does not exceed a certain temperature, otherwise, a certain amount. Otherwise, the packaging will melt and there will be some serious damage. So these are that's the source of these temperature envelopes that might be imposed on a system like this. What to do about it is a very interesting problem. Even though these issues are physical, this is a physics matter, right? The heat and temperature and heat flow, such things, even though they are physical, as it turns out, due to the various levels of abstraction, we can treat some of them pretty much as a computer science problem and a data transfer problem, for example. That's the specific example that I'll point out today. So the temperature here is determined by power density. It is not merely the total power. The total power actually might be within the budget, and yet your temperature might go off the budget because this is a slightly different metric here. Power density refers to power per unit area. Right. So if it happens that there are small components that are heavily used, for example, a register file is such a component in a processor. There might be other components depending on what you're doing in our system. But power per unit area is obviously a different metric, and that profile may be very different for different parts of the chip. There may be large parts of the chip that are relatively cool, but there may be some parts that are hot, and that's what we are worried about, and we need to do something explicitly about, because otherwise there would be some kind of a thermal runaway, because there is often a positive feedback loop between temperature and power that I will get to, but you can see that this power density came up from nowhere. This is not something that we were optimizing for earlier, and we need to introduce that awareness now in all over our chain, all the way from hardware from hardware to software and so on. A lot of this awareness is necessary, and now we have to inject that awareness in these different phases of the design. Okay, so let's look at a specific example just to get some appreciation. This is some work that we have been doing, and in fact we'll explore this more in the lab session today in the afternoon. We'll take a look at, we'll try to simulate some of these systems and try to understand what's going on. It is some view of the issues that come up, but let's look at what happens in in a CPU system that is working with a 3D memory, because these are new technologies, very fascinating, interesting new technologies that people are working with. Emerging memory technologies are a hot field from a device point of view, circuits point of view, but all the way to architecture and software point of view. How to best exploit these technological ideas is an important challenge today. But what I'll point out is that there are also, these are not merely performance challenges. In addition to performance, there are other issues, and temperature is a very interesting issue that comes up in a context like this. What is this 3D memory? This is essentially a stacked main memory DRAM system. So it consists of stacked dies. Each of these is a regular dies, but it is you stack them up vertically in this way, and they are connected through what are called through silicon vias. So what you have at one level, one horizontal plane, is a regular DRAM die, but they are connected in the ways that there is some innovation here in their connectivity. This is what they call a through silicon via. So that's the interconnect that they use for connecting and allowing communication across the horizontal layers. So why do all this? Essentially, this is good from the point of compactness. It is good from the point of bandwidth. Higher memory bandwidth can be delivered by a system like this. Latency also turns out to be low, so it is faster. So although not that much faster perhaps, but the biggest advantage here is the bandwidth, but there is also a compactness related advantage. If the same 8 chips here were to be 8 dies here and chips were to be laid out in a 2D system on a printed circuit board, it would occupy a lot more area and volume, whereas here, if they were all fabricated together into a 3D structure, it would be a lot more compact. Even though this is an exaggeration, what you see here in the picture, the height of a real 3D memory nowadays is only a few millimeters. The width and the profile here, right? The length and the width might be something like of the order of centimeters, but the height is only a few millimeters. So you can see this is a lot more compact structure than if you were to lay out the whole thing, the 8 different layers as separate chips on a printed circuit board. For now, that cost is higher, but of course, that is what is the well-known trajectory. If this is still intermediate stages. It's early stages for emerging technologies like this. They are being used today. In the industry, there are standardization efforts, including the HMC. That's the example that I showed there. But nevertheless, newer ones corresponding to HBM are the ones that are popular today. The technologies are similar. Conceptually, they are similar, but there are a lot of differences in the way the channel mapping and all of that has happened. These products are being made by major manufacturers today, and they are used in various contexts. Maybe not yet standard laptops and desktop kind of a system, but in various other products we have seen these getting introduced in GPUs, in FPGA systems, and so on. Right. So it's something that shows a lot of promise. Various kinds of stacking configuration you can think of. Maybe it's a CPU that is packaged in this, so it's combined in the same package along with a 3D DRAM. That could be one. It could also be the other way. Some of these are studied in research. Not all of them are there commercially, but you could stack the memory in various ways on the CPU. You could stack the CPU in one layer, the cache in one layer. So so the second and the third might be only in principle, but something like this one, which is CPU and stacked DRAM connected through a silicon interposer. These are systems that industry is trying out today. Okay, so that being the context, let's look at this 3D memory and identify some of these issues. We said there is a thermal issue. Where is the thermal issue? Now, let's assume that I have uniform load and activity somehow. So that uniform activity leads to uniform dynamic power, because dynamic power is a function of activity. So I have here my memory channels and the ranks of the memory that are distributed in this way here. So this is like a 4x4 grid. The horizontal layer is a 4x4 grid, so it is like 16 channels are there. This is a vertical channel. This example I'm talking about here is an HMC example, but it's not very different. So the mapping is different, but the ideas are not very different. So here's what happens. There is the dynamic power. There is also leakage power. That is actually an interesting component here. That leakage power actually increases with temperature. It's higher at higher temperature. And the problem is that if the temperature exceeds a certain threshold anywhere, right, then you need to do something drastic about it, because there is the danger of a thermal runaway. Thermal runaway means that there is a positive loop that might go out of control. What positive loop? If your temperature rises, then the leakage power rises. If the leakage power rises, then the temperature rises further. So that way there is a positive loop that if you are not careful about, and if you don't monitor and actively intervene, then the system might risk being burnt or something like that. Something drastic might happen. So we need to put some temperature awareness and exercise control in a very fine-grained way to make sure that the systems are operational. Okay, so here's our system. Maybe I have my 8 layers. I have that previous picture that I had. We have just abstracted out into these layers. There's a PCB at the bottom, and maybe there's a heat sink or whatever form of heat spreader or whatever way that there is a heat dissipation that's happening from the top. Okay. So here's a sort of an animation of what might go on. The heat flows into that heat sink from the top here, and because these layers, the layers at the top are actually next to the heat sink, there is a better heat dissipation. But from the bottom, the heat dissipation is not so good, because there is no real serious path of the heat downward. So here the real heat spreading is happening only upwards. So there is a gradation that you see. That is something that we have to be aware of. So vertically, this is not the temperature is not constant. The temperature is actually higher towards the lower part of the system. There are some other interesting effects, even horizontally, even within the same channel. There is a difference between the temperature of the central channels and the external channels for the same reasons. Each of the central channels is surrounded by more other ranks, and therefore there is a slight temperature variation here too, right? So, but the vertical one is the one that's more important. What can we do, knowing that such effects are there? Maybe, so I could do various things, but one of the simplest things, just conceptually simplest things, is I could back up data to an external 2D memory, which is a regular DRAM, DDR, and maybe in the process shut down some of these channels. Now that is bad from a performance point of view, but still it allows some part of the computation to proceed. So it is still not as bad as shutting down the whole system. So this is some intermediate solution where performance is compromised, but you don't completely shut the system down. So those central channels are turned off. And secondly, what might happen is that, okay, you go on for some time, because the central channels are turned off, the adjacent channels to those now have an opportunity to reduce the temperature, but the corner ones, because they are still further from the center, they might be even hotter, and they might exceed the temperature threshold. And therefore, maybe as a second stage, I can back up some of the corner data off again into my backup. So some such mechanism I could use, some policy I could use to make sure that we extract some performance from the system in spite of the system getting hot, and just to make sure that no part of the system exceeds the threshold that is imposed on the system. Okay, so what I would like to conclude with is a simulation environment. This is something that we would like you to experiment with in the afternoon today. So this is a tool that integrates several simulations simultaneously going on. There is a performance simulation. That tool is called Sniper. All of these are open source tools that we spent some effort in putting together and understanding how a system with an emerging memory technology like a 3D memory working with a processor might how does it behave, and what does the temperature profile of the system. So the CPU, so it consists of an integrated performance simulator, the thermal simulator tool like Hotspot is what a lot of people, researchers use to understand the thermal behavior, thermal profile of chips. A memory area performance and power modeling tool called Cacti that is again heavily used in academia and research to reason about various configurations of memories and caches. Finally, all of these things can be taken into account in a high-level decision making by a task scheduler or something like that. So these tools were put together into what is what we are calling Comet, where some kind of a visualization is possible. You'll see that visualization because the output of that simulation is a video, a simple video of what is happening in each of these layers that can be useful. What's shown in the right here is essentially an expansion of that lowermost layer, just to give a better view of what's happening. What you are interested in is what's happening across these layers. Within the layer, again, what is the distribution of temperature, so that that gives some idea at the system level of the implications of whatever it is that of whatever set of programs that we are trying to do, or the implications of a policy that we are trying to impose on the system in our effort to balance the performance with the power and temperature. What sort of things can we do? We can analyze the temperature profile of the system of various configurations. It could be stacked in various ways, but particularly this separately 3D memory CPU is there. With that, a 3D memory structures is there. This is sort of a new tool that we put together. It's in a multi-institutional effort where there was it was primarily led by us, but there were also significant contributions from University of Amsterdam and Karlsruhe, where these the tools, some of these were existing tools. That Hot Sniper was a tool from Karlsruhe and Amsterdam, and these other tools that we had, we put together into a system that is still early in its usage, but still we have played with it a little bit, and some very interesting early observations we have made that we have tried to translate into some interesting policies that we can control. What kind of things can we do with it? We can maybe implement some dynamic thermal management policies. That's an example that we'll look at in the afternoon today. But you could do other sophisticated things like task scheduling, CPU frequency scaling, memory power state, all of these things, policies we can come up with that are aware of what's happening in the system, and also responding and trying to control different aspects so that overall we are able to extract our performance power that we want from the system. So let me summarize here the thermal parts. I didn't get to too much detail here. Obviously, this is not the only interesting thermal topic. There are many other things. Processor itself is a very interesting subsystem from a thermal point of view. It is just necessary nowadays to play this game of shutting down part of the system, keeping only part of the system on. So even though there are a lot of resources all the resource cannot be simultaneously utilized because of various reasons, because of the energy profile, energy envelope, because of temperature envelope, and all of these force intelligent play with respect to shutting down parts of the system and keeping some other parts on, slowing down parts of the system. These are important things that are areas of ongoing research. So these concerns are emerging as important topic for us. Of course, these are opportunities. These challenges should be seen as opportunities, research opportunities for us to intervene at the system level. And among other things, I want to point out that almost all this research is done all over the world on open source platforms, various simulation platforms, such as the one that I just pointed out today. That too, we have released on the open source. You are welcome to play with that. More details of that we'll discuss in the lab today. Let me just conclude saying that this work that I talked about, a lot of our group research scholars have contributed to it, but in general we've been looking at areas like cache management, emerging 3D memory technologies, like emerging memory technologies like 3D memory, non-volatile memory, and some other newer transistor technologies like negative capacitance, NC FET, what's called, and various other things, design automation and hardware acceleration. So this is sort of a summary of the kind of research work that's happening. Let me conclude here. I managed to finish in time. Again, I should apologize for the late start, but thank you for your patience. And if you have maybe questions, if there is any time for handling questions, I could take some. Thanks.
Thank you, Dr. Preeti. We definitely have time for questions. Please go ahead if there are any questions.
Sir, what is difference between using a simulator and just typing a command like sensors in a terminal to get the power of currently in the course?
Typing in the terminal means we are working on a real system, right? So if I say I want to get the temperature of a certain component, and the operating system has permitted me to examine that in some way, then I type that command and I observe what is going on. Now, what's happening in the simulator is that this is a software emulation of a system that is currently not there. When I say 3D, we are studying a 3D memory system or some other memory technology. This is an advanced technology that is not yet there. Our machine is not made of that system. So we are studying the implications by using a software model of the system. So it is a processor model that is running. It is a memory model that is there. All of these are just software models. And what we are doing is, okay, if I run this bunch of 10 instructions or 10 million instructions, those instructions I try to interpret them according to the model that I have, both with respect to performance and with respect to power. What is the performance model? It might be that, okay, this instruction takes 10 takes 2 nanoseconds. This other instruction takes 3 nanoseconds. That is a performance model, right? And similarly, the power model might be that, okay, this if I run this instruction, so much energy, this is an energy model, right? So much energy is consumed. If I run that other instruction, then so much energy is consumed. So per unit time, when I run those 10 instructions, that is the average power, that is the total energy. So this is happening in a simulation. It is not the real system that we are running on and measuring, but this is a software version of it. it's just that the system doesn't exist yet. Maybe it's a more advanced technology. The commercial implementations might not even be there, and yet we would like to study what is the implication, right? What is the impact of running this program on this futuristic system that I have, or if I change some architecture, then what is the impact? So these kind of studies are typically done in the context of a simulator, because it is just, to us, it is in the simulator, it is relatively easy to set up a new architectural feature, or even a new, when we say emerging memory technology, what do we mean here? Maybe it is just a bunch of numbers, right? It is a bunch of energy numbers. If you access it, then you say that, okay, so many nanojoules are accessed. This is a model of the memory system that is used in the simulator. So yeah, that's what it is. It is not the real program
yes, sir, yes,
that is running on a real system.
yes, sir. Understood, sir.
Are there any more questions?
Sir, one more question. Nowadays in new laptops, I can see there is no fan. Means what kind of heat sinks they are using? Means there is no, in earlier laptops or earlier systems, I used to see fans. Yeah. But in new systems there is no fan there. But
yeah, see, what happens is there would usually be some heat spreader, sort of a mechanism covering the chip. But essentially what it translates to, if you don't have a fan, what is the difference between having a fan and not having a fan, is that somehow the heat dissipation is better if the fan is there. Okay, just because the airflow is better, because the convection that it induces. If the fan is not there, then that means that that much airflow is not possible, and therefore the heat dissipation abilities reduces of the system. So there's not much more that is happening. But if you remove the fan or any such advanced heat sink kind of features, all that is happening is now you have curtailed the power dissipation of the system. So earlier, let's say you were able to afford a 200-watt processor because a fan was there. Now, if you say that you're not going to allow a fan, then you are going to reduce it. Maybe you say that, okay, now your processor can take only 50 watts or something like that. You tighten the power budget. It is okay. It's just that at higher power dissipations, you need the fan. At a lower power dissipation, you don't need the fan. But of course, that translates to a constraints. Now the system has to deliver good performance in the absence of such heat dissipation abilities. So the envelope has reduced. Now the budget has become more constrained. That is the implication. Our phones, of course, don't have fans and any such sophisticated features, right, for heat dissipation. What does that translate to? It means that there is a strict imposition. There also we have memories and processors and so on, but maybe the phone is not allowed to dissipate more than 4 watts or 5 watts or some such very small number. So otherwise it is okay. It's just that you have now, this comes as a design constraint. It means that whatever you do, you have to obey the budget, the power budget, because otherwise the system will melt down. So that's really all that is this translates to. So they removed the fan. They didn't put anything more sophisticated. It's just that they removed the fan and translated that into a stringent power budget, which of course designers have nicely responded to by introducing all kinds of advanced power optimizations into their system. You see that what that would have resulted in is that, okay, the individual processors are not as fast as they used to be. We studied that in the previous lectures also, right? That individual processors are getting indeed slower to some extent, but we are making up by other things. Throughput is increasing, more of them are there, parallelism is there. So yes, in fact, to conclude, removing the fan, it was not replaced by anything. In fact, it was replaced by nothing and just passed down as a power constraint to the designer.
Yes, sir. Thank you, sir. Understood. Thank you, sir.
Sir, which is the less power consuming in compared to matrix multiplication implementation or vector multiplication implementation in hardware?
No, vector. Oh, okay. You mean instead of a matrix multiplication? So when you say vector multiplication, what do you mean? Is it just the corresponding elements of the vector are multiplied?
Yes, sir. Like in programming,
Yeah.
different programmings, we use vector multiplication instead of matrix multiplication. Then the programming becomes efficient in performance. So we can implement in hardware also that kind of.
Okay, no, actually, this is hard to say without the context because, of course, this should be architecture dependent, right? Even matrix multiplication, how it is implemented really is the question, right? What is the basic unit with the help of which you are expressing, with the help of which you are doing the matrix multiplication? This is a very general, mathematically, it is a common statement, but there are hundreds of different implementations, some of which are just software implementations because you can transform in various ways, you can tile the matrix, and you can do interchanging. So these are just compiler level interventions. But that's only one part. That is if you don't touch the hardware. But you could do various things at the hardware level. You could just use a standard processor, but then you can have customized hardware that is that's doing only matrix multiplication and nothing else. So the more custom it is, the more efficient it would be. If it is designed for performance, then you can expect the best performance. If it is designed for power, so similar, it depends on what the objective is, and we would respond accordingly. So I think it is hard really to say which is more efficient because clearly it depends on what is the underlying architectural platform, and a high level mathematical function like a matrix multiplication, how efficient the power is clearly translates to what is the set of sub actions that you are going to perform to implement that matrix multiplication. So really it is in that detail. I don't think in some sense it is possible to say which is more power efficient. Now, power is one thing, right? It is just, remember, it's energy per unit time. The other thing is energy efficient, which is more work. Energy, the matrix, one function is more energy efficient than the other. Other things remaining the same. This it is possible to say more about. Let us say you fix the architectural space or something like that, and if you count the number of operations and those number of operations are different, then that gives a hint as to which one would be more, which one would take more energy, which is less energy. In fact, you could abstract out everything and also analyze in terms of just asymptotic complexity. As the size of the matrix becomes large, maybe there is a difference. But sometimes that is misleading, of course, so that's just a theoretical picture. But once a reasonable model is there of the system, it is possible to predict in a more efficient way, possibly. I mean, one of the first step is to come up with a reasonable model. Really, that's the first step, both with respect to performance and also with respect to energy, so that we can then take the next step, like how our more complex function translates to the elementary functions that are available to us, for which a model is there with respect to energy and with respect to performance. And maybe at the end only I can make a reasonable power computation and say that this is more power efficient or this is more energy efficient. So yeah, unfortunately it is not that easy. Just from the functionality, there is no way we can say which is more power efficient. The energy efficiency we can say a little bit about because maybe there is some difference in the complexity of the operations, but a lot actually depends on the architectural platform on which we are going to be implementing it.
Yes.
All right. So thank you, Dr. Preeti. Looks like there may be more questions in the afternoon session. Then
Sure.
Thank you, and we
Okay,
look
thank you.
forward to the session in the afternoon.
Sure. Bye.
Thank you. Bye. For the students, as you're aware, we'll meet back at 12 o'clock for the next session by Dr.